Chapter 9. Carbon Compounds. Students, in this chapter, we shall study important points like bonds in carbon compounds, hydrocarbons, functional groups and homologous series, chemical properties of carbon compounds, carbon, a versatile element, nomenclature of carbon compounds, macromolecules and polymers. We shall study these topics in details. Can you recall? 1. What are the types of compounds? Answer. Organic and inorganic compounds are the two important types of compounds. 2. Objects in everyday use such as foodstuff, fibers, paper, medicines, wood, fuels are made up of various compounds. Which constituent elements are common in these compounds? Answer. Carbon is the common element found in all above-mentioned objects of everyday use. 3. To which group in the periodic table does the element carbon belong? Write down the electronic configuration of carbon and deduce the valency of carbon. Answer. Carbon belongs to group 14 in the periodic table. Its atomic number is 6 and its electronic configuration is 2,4. Hence, its valency is 4. In the previous standards, we have seen that organic and inorganic compounds are the two important types of compounds. Except materials fabricated from metal and glass or soil, several other materials from foodstuff to fuels are made up of organic compounds. The essential element in all the organic compounds is carbon. About 200 years back, it was believed that organic compounds are obtained directly or indirectly from the organisms. However, after synthesis of the organic compound urea from inorganic compounds in the laboratory, the organic compounds received a new identity as carbon compounds. All the compounds having carbon as a constituent element are called as organic compounds. The compounds carbon dioxide, carbon monoxide, carbide salts, carbonate salts and bicarbonate salts are exception. They are inorganic compounds of carbon. Bonds in carbon compounds. You have learnt about the ionic compounds in the previous chapter. You have seen that ionic compounds have high melting and boiling points, and they conduct electricity in the molten and dissolved state. You have also seen that these properties of ionic compounds are explained on the basis of the ionic bonds in them. The following table shows melting and boiling points of a few carbon compounds. Are these values higher or lower as compared to the ionic compounds? Generally, the melting and boiling points of carbon compounds are found to be lower than 300 degrees Celsius. From this, we understood that the intermolecular attractive forces are weak in carbon compounds. In the previous standard, on testing the electrical conductivity of carbon compounds, glucose and urea, you have observed that they are not electrical conductors. Generally, most of the carbon compounds are found to be bad conductors of electricity. From it, we understand that structures of most of the carbon compounds lack ionic bonds. It means that the chemical bonds in carbon compounds do not produce ions. Can you tell 1. What is meant by a chemical bond? Answer. A chemical bond is an attraction force between atoms, ions, or molecules that allows the formation of various chemical compounds which contains two or more atoms. 2. What is the number of chemical bonds that an atom of an element forms called? Answer. The chemical bonds that an atom of an element forms is single, double, and triple bond. 3. What are the two important types of chemical bonds? Answer. There are two main types of chemical bonds that hold atoms together: covalent and ionic or electrovalent bonds. Electronic configuration. In the previous standards, you have learnt about the relationship between electronic configuration and valency of an element, and also about the ionic and covalent bonds. Let's see all the background of electronic configuration of carbon and the covalent bonds formed. Carbon atom C6 has an electronic configuration of 2, 4. The number of electrons in the valence shell are 4. Nearby noble gas and their electronic configuration is helium, He, with electronic configuration 2, neon, Ne, with electronic configuration 2, 8. You have seen that the driving force behind the formation of bond by an atom is to attain the stable electronic configuration of the nearby noble gas and obtain stability. As the valence shell of carbon contains 4 electrons, there can be many alternative routes to attain a noble gas configuration. First, to attain the configuration of noble gas helium, He, by losing one after another all the 4 valence electrons. In this method, the net positive charge on the carbon atom goes on increasing during loss of every electron. Therefore, to lose the next electron, more energy is required, which makes the task more difficult. Moreover, the C4+ cation that would ultimately form in this process becomes unstable in spite of its noble gas configuration because it has a small size with high net charge. Therefore, carbon atom does not take this route to attain a noble gas configuration. Second, to attain the stable configuration of the noble gas neon, Ne, by accepting one by one all the 4 electrons in the valence shell. In this method, the net negative charge on the carbon atom goes on increasing while accepting every new electron. Therefore, more energy is required for accepting the next electron by overcoming the increasing repulsive force, making the task more and more difficult. Moreover, the C4- anion ultimately formed would be unstable in spite of its noble gas configuration, as it would have a small size with high net charge, making it difficult for the nuclear charge +6 to hold 10 electrons around it. Therefore, carbon atom does not take this route to attain a noble gas configuration. Third, to attain the configuration of neon by sharing 4 electrons of valence shell with 4 valence electrons of other atoms, In this method, two atoms share valence electrons with each other. Valence shells of both the atoms overlap and accommodate the shared electrons. As a result, both the atoms attain a noble gas configuration without generating any net charge on them, which means that atoms remain electrically neutral. Due to these factors, atoms attain stability. Therefore, carbon atom adopts this route to attain a noble gas configuration. Covalent bond. The chemical bond formed by sharing of two valence electrons between the two atoms is called covalent bond. A covalent bond is represented clearly by drawing an electron dot structure. In this method, a circle is drawn around the atomic symbol and each of the valence electrons is indicated by a dot or a cross. The covalent bond formed between the atoms is indicated by showing the circles around the atomic symbols crossing each other. The shared electrons are shown in the overlapping regions of the two circles by dot or cross. The electron dot structure is also drawn without showing the circle. One pair of shared electrons constitutes one covalent bond. A covalent bond is also represented by a small line joining the symbols of the two atoms. The line structure is also called structural formula. Let us first look at the hydrogen molecule, which is the simplest example of a molecule formed by covalent bonding. You have already learned that the atomic number of hydrogen being 1, its atom contains 1 electron in K shell. It requires one more electron to complete the K shell and attain the configuration of helium He. To meet this requirement, two hydrogen atoms share their electrons with each other to form H2 molecule. One covalent bond, that is a single bond, is formed between two hydrogen atoms by sharing of two electrons. The O2 molecule is formed by chemical combination of two oxygen atoms. An N2 molecule is formed by the chemical combination of two nitrogen atoms. On drawing the electron dot structures of these two molecules, it becomes clear that the two oxygen atoms in O2 molecule are joined with each other by two covalent bonds, that is, a double bond, while the two nitrogen atoms in the N2 molecule are joined with each other by three covalent bonds, that is, a triple bond. Now, let us consider carbon compound methane CH4. You have learnt about the occurrence, properties and use of methane molecule in the previous standard. Hope you remember. Just now, we saw that carbon atom forms 4 covalent bonds using the 4 valence electrons and attains the configuration of the nearby noble gas neon, Ne, and obtains stability. This figure shows the line structure and also the electron dot structure of methane. Do you know? To understand the structures of carbon compounds, various types of molecular models are used. The figure shows ball and stick model and space-filling model of methane molecule. Use your brain power. 1. Atomic number of chlorine is 17. What is the number of electrons in the valence shell of chlorine? Answer. Atomic number of chlorine is 17. The electronic configuration of chlorine is 287. The last shell of a chlorine atom has 7 electrons in it. Therefore, there are 7 valence electrons in a chlorine atom. 2. Molecular formula of chlorine is Cl2. Draw electron dot and line structure of a chlorine molecule. The electron dot structure and line structure of a chlorine molecule should be drawn in this way. 3. The molecular formula of water is H2O. Draw electron dot and line structures for this triatomic molecule. Use dots for electron of oxygen atom and crosses for electrons of hydrogen atoms. You can draw electron dot and line structures for water in such a way. 4. The molecular formula of ammonia is NH3. Draw electron dot and line structures for ammonia molecule. Here are the electron dot and line structures for ammonia molecule. Use your brain power. 1. The molecular formula of carbon dioxide is CO2. Draw the electron dot structure without showing circle and line structure for CO2. Answer. This is electron dot structure and line structure for CO2. 2. With which bond C atom in CO2 is bonded to each of the O atoms? Answer. C atom in CO2 is bonded to each of the O atom by covalent bonds. 3. The molecular formula of sulfur in S8, in which 8 sulfur atoms are bonded to each other to form one ring. Draw an electron dot structure for S8 without showing the circles. Here is electron dot structure for S8 without showing the circles. Carbon, a versatile element. We saw that carbon atoms, like some other atoms, share the valence electrons to form covalent bonds. Similarly, we also saw the structure of the simple carbon compound, methane. But carbon is different than the other elements. The number of compounds formed from carbon is extremely large. In the beginning, we saw that except for the objects formed from metals and glass or soil, all the other objects are made from carbon. In short, the entire living kingdom is made from carbon. Our body is also made from carbon. Millions of molecules ranging from the small and simple methane molecule to the extremely big DNA molecule are made from carbon. The molecular masses of carbon compounds range up to 10 raised to 12. This means that carbon atoms come together in a large number to form extremely big molecules. What is the cause of this unique property of carbon? It is due to the peculiar nature of the covalent bonds formed by carbon. It can form large number of compounds. From this, we come to know the following characteristics of carbon. Let's have a look. Characteristics of carbon. A. Carbon has a unique ability to form strong covalent bonds with other carbon atoms. This results in formation of big molecules. This property of carbon is called catenation power. The carbon compounds contain open chains or closed chains of carbon atoms. An open chain can be a straight chain or a branched chain. A closed chain is a ring structure. The covalent bond between two carbon atoms is strong and therefore stable. Due to the strong and stable covalent bonds, carbon is bestowed with catenation power. Till now, the number of known carbon compounds is about 10 million. This number is larger than the total number of compounds formed by all the other elements. The range of molecular masses of carbon compounds is 10 raised to 1 to 10 raised to 12. Observe the table given next. Use your brain power. 1. Hydrogen peroxide decomposes on its own by the following reaction. HOOH, that is, hydrogen peroxide, decomposes into 2HOH, that is, water molecule plus O2. From this, what will be your inference about the strength of OO covalent bond? Answer. The strength of OO covalent bond is weaker. 2. Tell from the above example whether oxygen has catenation power or not. Oxygen shows very less tendency towards catenation. Oxygen links its two atoms in peroxides only. Here's a table showing carbon compounds and their molecular masses. Methane, CH4, the smallest carbon compound, has a molecular mass of 16. Cooking gas, C3H8, has molecular mass 44 and C4H10 has molecular mass 58. Benzene, C6H6, has molecular mass 78. Camphor, C10H16 or 152. Penicillin, C16H18N2O4S, molecular mass 334. Sugar, C12H22O11, 342. Sodium dodecyl benzene sulfate, a detergent, has molecular mass 347. Fat has molecular mass approximately 700. Starch, approximately 10 raised to 3. Cellulose, approximately 10 raised to 5. Protein, approximately 10 raised to 5. Polyethylene, approximately 10 raised to 6. DNA, molecular mass approximately 10 raised to 12. B. Two carbon atoms can be bonded together by 1, 2 or 3 covalent bonds. These are called single bond, double bond and triple bond respectively. Due to the ability of carbon atoms to form multiple bonds as well as single bonds, the number of carbon compounds increases. For example, there are 3 compounds, namely ethane, CH3, single bond CH3, ethene, CH2, double bond CH2, and ethyne, CH, triple bond CH, which contain 2 carbon atoms. C. Being tetravalent, one carbon atom can form bonds with 4 other atoms, carbon or any other. This results in formation of many compounds. These compounds possess different properties as per the atoms to which carbon is bonded. For example, 5 different compounds are formed using 1 carbon atom and 2 monovalent elements, hydrogen and chlorine. CH4, CH3Cl, CH2Cl2, CHCl3, CCl4. Similarly, carbon atoms form covalent bonds with atoms of elements like O, N, S, halogen, and P to form different types of carbon compounds in large number. D. Carbon has one more characteristic which is responsible for large number of carbon compounds. It is isomerism. Shortly we will learn about it. Hydrocarbons, saturated and unsaturated. Carbon compounds contain many elements. The element hydrogen is present to a smaller or larger extent in majority of carbon compounds. The compounds which contain carbon and hydrogen as the only two elements are called hydrocarbons. Hydrocarbons are the simplest and the fundamental organic compounds. The smallest hydrocarbon is methane, CH4, formed by combination of one carbon atom and 4 hydrogen atoms. We have already seen the structure of methane. Ethane is one more hydrocarbon. Its molecular formula is C2H6. The first step in writing the line structure, that is, structural formula of a hydrocarbon, is to join the carbon atom in the molecule with single bonds, and then in the second step, use the hydrogen atoms in the molecular formula so as to fulfill the remaining valencies of the tetravalent carbon atoms. This figure shows electron dot structure using two methods. Ethane, molecular formula C2H6. Step 1. Join the two carbon atoms with single bonds, C, single bond C. Step 2. Use the 6 hydrogen atoms in the molecular formula for fulfilling the tetravalency of both the carbon atoms. Use your brain power. Molecular formula of propane is C3H8. From this, draw its structural formula. The structural formula of propane can be drawn in this way. From the structural formula of ethane and propane, it is seen that the valencies of all the atoms are satisfied by the single bonds. Such compounds are called saturated compounds. Ethane and propane are saturated hydrocarbons. Saturated hydrocarbons are also called alkanes. There are 2 more hydrocarbons that contain 2 carbon atoms, namely ethene, C2H4, and ethine, C2H2. Let us see the method to draw the structural formula, that is line structure of ethene, C2H4. Step 1. Join the 2 carbon atoms with single bond, C single bond C. Step 2. Use the 4 hydrogen atoms in the molecular formula for satisfying tetravalency of both the carbon atoms. It appears that one valency of each of the 2 carbon atoms is not satisfied. Step 3. Satisfy the tetravalency of the 2 carbon atoms by drawing a double bond in place of the single bond between them. Use your brain power. 1. The molecular formula ethine is C2H2. From this, draw its structural formula, an electron dot structure. The structural formula in electron dot structure of ethine, C2H2, can be drawn in this way. 2. How many bonds have to be there in between the 2 carbon atoms in ethine so as to satisfy their tetravalency? Answer: there has to be a triple bond in between the two carbon atoms in ethyne so as to satisfy the tetravalency. Unsaturated compounds. The carbon compounds having a double bond or triple bond between two carbon atoms are called unsaturated compounds. Ethene and ethyne are unsaturated hydrocarbons. The unsaturated hydrocarbons containing a carbon-carbon double bond are called alkenes. The unsaturated hydrocarbons whose structures contain a carbon-carbon triple bond are called alkynes. Generally, the unsaturated compounds are more reactive than the saturated compounds. Straight chains, branched chains, and rings of carbon atoms. Let us compare the structural formulae of methane, ethane, and propane. From these structural formulae, it is seen that the carbon atom, single or more carbon atoms bonded to each other, lie in the core of the molecule, while the hydrogen atoms bonded to each of the carbon atoms are on the periphery of the molecule. The mutually bonded carbon atoms in the core are like the skeleton of the molecule. The carbon skeleton determines the shape of the molecule of a carbon compound. A straight chain of carbon atoms is formed by joining the carbon atoms one next to the other. Complete the table. The first column of the table shows straight chains of carbon atoms. Write the structural formulae of the corresponding straight chain hydrocarbons in the second column, satisfying the tetravalency of the carbon atom by joining them to hydrogen atoms. Work out the molecular formula for this and write it down in the third column. The name of the hydrocarbon is given in the fourth column. The straight chain of carbon atoms, C. This is the structural formula. Its molecular formula is CH4. Name is methane. Straight chain, C, single bond C. This is the structural formula. Molecular formula is C2H6. Name, ethane. Straight chain of carbon atoms is C, single bond C, single bond C. This is the structural formula. Molecular formula C3H8. Name, propane. Straight chain of carbon atoms C, single bond C, single bond C, single bond C. This is the structural formula. Molecular formula C4H10. Name, butane. Straight chain of carbon atoms C, single bond C, single bond C, single bond C, single bond C. This is the structural formula. Molecular formula C5H12. Its name is pentane. Straight chain of carbon atoms is C, single bond 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 C. This is the structural formula. Molecular formula C6H14. Name is hexane. Straight chain of carbon atoms is C, single bond 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 C. This is the structural formula. Molecular formula is C7H16. Name is heptane. Straight chain of carbon atoms is C, single bond 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 C. This is the structural formula. Molecular formula is C8H18. Name is octane. Straight chain of carbon atoms is C, single bond 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 C. This is the structural formula. Molecular formula is C9H20. Name is nonane. Straight chain of carbon atoms is C, single bond 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 C. This is the structural formula. Molecular formula is C10H22. Name is decane. Do you know? In the course of millions of years, the reserves of crude oil were formed from the dead organisms buried under the sea floor. This crude oil and natural gas are now recovered from the oil wells. The natural gas is mainly methane. The crude oil is a complex mixture of thousands of different compounds. It mainly contains various hydrocarbons. Various useful components such as CNG, LPG, petrol, that is gasoline, kerosene, diesel, engine oil, lubricant, etc. are obtained by separation of crude oil using fractional distillation. Now let us pay more attention to the carbon chain in butane. The 4 carbon atoms can be joined to form a carbon chain in yet another way. 2 different structural formulae are obtained on joining hydrogen atoms to these 2 chains so as to satisfy the tetravalency of the carbon atoms. The molecular formula of both these structural formulae is the same, which is C4H10. These are 2 different compounds as their structural formulae are different. The phenomenon in which compounds having different structural formulae have the same molecular formula is called structural isomerism. The number of carbon compounds increases further due to the isomerism observed in carbon compounds. The carbon chain, first, is a straight chain of carbon atoms, whereas the carbon chain, second, is a branched chain of carbon atoms. Apart from the straight chains and branched chains, closed chains of carbon atoms are present in some carbon compounds, wherein rings of carbon atoms form. For example, the molecular formula of cyclohexane is C6H12 and its structural formula contains a ring of 6 carbon atoms. Use your brain power. Draw electron dot structure of cyclohexane. Here is electron dot structure of cyclohexane. Types of carbon compounds. All types of carbon compounds, whether straight chain, branched chain, or cyclic, can be saturated or unsaturated. This is explained by the various examples of hydrocarbons in the table. In straight chain hydrocarbons, saturated hydrocarbon is propane, C3H8, and unsaturated hydrocarbons are propene, C3H6, and propyne, C3H4. In branched chain hydrocarbons, saturated hydrocarbon is isobutane C4H10 and unsaturated hydrocarbon is isobutylene C4H8. In cyclic hydrocarbons, saturated hydrocarbons are cyclohexane C6H12 and cyclopentane C5H10. And unsaturated hydrocarbons are cyclohexene C6H10 and benzene C6H6. It is learned from the structural formula of benzene that it is a cyclic unsaturated hydrocarbon. There are 3 alternate double bonds in the 6-membered ring structure of benzene. The compounds having this characteristic unit in their structure are called aromatic compounds. Functional groups in carbon compounds. Till now you have learnt about the hydrocarbon compounds formed by combination of the elements carbon and hydrogen. Many more types of carbon compounds are formed by formation of bonds of carbon with other elements such as halogens, oxygen, nitrogen, sulfur. The atoms of these elements substitute one or more hydrogen atoms in the hydrocarbon chain, and thereby the tetravalency of carbon is satisfied. The atom of the element which is substitute for hydrogen is referred to as heteroatom. Sometimes heteroatoms are not alone but exist in the form of certain groups of atoms. The compound acquires specific chemical properties due to these heteroatoms or the groups of atoms that contain heteroatoms, irrespective of the length and nature of the carbon chain in that compound. Therefore, these heteroatoms or the groups of atoms containing heteroatoms are called functional groups. Table: Functional groups in carbon compounds. The table shows a few functional groups that occur in carbon compounds. Here, the free valency of the functional groups is indicated by a short line. The functional group taking place of hydrogen is joined to the carbon chain with its valency. The carbon-carbon double and triple bonds are also recognized as functional groups as the respective compounds get specific chemical properties due to them. Heteroatoms are halogen, that is chlorine, bromine and iodine, which are named as halo, that is chromo, bromo, iodo. The structural formula is XCl, Br, I, and condensed structural formula is XCl, Br, I. The heteroatom is oxygen. The functional group is 1. Alcohol. Its structural formula is OH. Its condensed structural formula is OH. 2. The functional group is aldehyde. Its structural formula is C double bond OH. Its condensed structural formula is CHO. 3. The functional group is ketone. Its structural formula is C double bond O. Condensed structural formula is CO. 4. The functional group is carboxylic acid. The structural formula is C double bond O single bond OH. Condensed structural formula is COOH. 5. The functional group is ether. Structural formula is O. Condensed structural formula is O. 6. The functional group is ester. Structural formula is C double bond O single bond O. Its condensed structural formula is COO. The heteroatom is nitrogen. The functional group is amines. Its structural formula is N single bond H single bond H. Its condensed structural formula is NH2. Homologous series. You have seen that chains of different lengths are formed by joining the carbon atoms to each other. Moreover, you have also seen that a functional group can take place of a hydrogen atom on these chains. As a result of this, large number of compounds are formed having the same functional groups but different length of carbon chain. For example, there are many compounds such as CH3OH, CH3CH2OH, CH3CH2CH2OH, CH3CH2CH2CH2OH, which contain alcohol as the functional group. Though the length of the carbon chains in them is different, their chemical properties are very much similar due to the presence of the same functional group in them. The series of compounds formed by joining the same functional group in the place of a particular hydrogen atom on the chains having sequentially increasing length is called homologous series. There are different homologous series in accordance with the functional group. For example, homologous series of alcohols, homologous series of carboxylic acids, homologous series of aldehydes, etc. All the members of the homologous series are homologues of each other. Earlier, you filled the structural formulae and molecular formulae in the table. From that, the initial part of the homologous series of alkanes was formed. Complete the table. Homologous series. Let us understand the characteristics of homologous series by considering initial parts of homologous series of alkanes, alkenes, and alcohols. Fill in the gaps in the table A, B, and C of homologous. A. Homologous series of alkanes. Methane. Its molecular formula is CH4. Condensed structural formula is CH4. Number of carbon atoms 1. Number of CH2 units 1. And boiling point in degrees Celsius is minus 162. Ethane. Molecular formula C2H6. Condensed structural formula CH3CH3, number of carbon atoms 2, number of CH2 units 2, boiling point minus 88.5 degrees Celsius. Propane, molecular formula C3H8, condensed structural formula CH3CH2CH3, number of carbon atoms 3, number of CH2 units also 3, boiling point minus 42 degrees Celsius. Butane, molecular formula C4H10, condensed structural formula CH3CH2CH2CH3, number of carbon atoms 4, number of CH2 units 4, boiling point 0 degrees Celsius. Pentane, molecular formula C5H12, condensed structural formula CH3CH2 CH2, CH2, CH3. Number of carbon atoms 5. Number of CH2 units 5. Boiling point 36 degrees Celsius. Hexane C6H14. CH3, CH2, 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 CH3. Number of carbon atoms 6. Number of CH2 units 6. Boiling point 69 degrees Celsius. Now let's have a look at the next table, B, homologous series of alcohols. We have the name, molecular formula, condensed structural formula, number of carbon atoms, number of CH2 units, and boiling point in degrees Celsius. Methanol, molecular formula CH4O, condensed structural formula CH3OH, number of carbon atoms 1, number of CH2 units 1, boiling point 63 degrees Celsius. Ethanol C2H6O, CH3CH2OH, number of carbon atoms 2, number of CH2 units 2, 78 degrees Celsius. Propanol C3H8O, CH3CH2 CH2OH, number of carbon atoms 3, number of CH2 units 3, boiling point 97 degrees Celsius. Butanol C4H10O, CH3CH2 CH2 CH2OH, number of carbon atoms 4, number of CH2 units 4, boiling point 118 degrees Celsius. C, homologous series of alkenes. Ethene, molecular formula C2H4, condensed structural formula CH2 double bond CH2, number of carbon atoms 2, number of CH2 units 0, boiling point minus 102 degrees Celsius. Propene C3H6, condensed structural formula CH3, CH double bond CH2, number of carbon atoms 3, number of CH2 units 1, boiling point minus 48 degrees Celsius. 1-butene, molecular formula C4H8, condensed structural formula CH3CH2 CH double bond CH2, number of carbon atoms 4, number of CH2 units 2, boiling point minus 6.5 degrees Celsius. 1-pentene, molecular formula C5H10, condensed structural formula CH3CH2 CH2 CH double bond CH2, number of carbon atoms 5, number of CH2 units 3, boiling point 30 degrees Celsius. 9.17, some homologous series. Use your brain power. 1. By how many CH2, that is methylene units, do the formulae of the first two members of homologous series of alkanes, methane, CH4, and ethane, C2H6, differ? Similarly, by how many CH2 units do the neighboring members, ethane, C2H6, and propane, C3H8, differ from each other? Answer: there is difference of one CH2 group in neighboring members of homologous series. 2. How many methylene units are extra in the formula of the fourth member than the third member of the homologous series of alcohols? Answer: 1 methylene unit is extra in the formula of the fourth member than the third member of the homologous series of alcohols. 3. How many methylene units are less in the formula of the second member than the third member of the homologous series of alkenes? Answer: 1 methylene unit is less in the formula of the second member than the third member of the homologous series of alkenes. You have found that in any homologous series, while going in an increasing order of the length of the carbon chain, every time one methylene unit, that is CH2, goes on increasing. Therefore, while going in an increasing order of the length, there is a rise in the molecular mass of the members by 14 Dalton. Inspection of the table A, B and C will reveal one more point to you, and that is gradation in the boiling points. Boiling point is a physical property of a compound. Generally, it is found that while going in an increasing order in any homologous series, the physical properties show variation in one direction. That is, a gradation is observed in the physical properties. Use your brain power. 1. The table shows the homologous series of alkenes. Inspect the molecular formulae of the members of this series. Do you find any relationship in the number of carbon atoms and the number of hydrogen atoms in the molecular formulae? Yes, there is a relationship in the number of carbon atoms and the number of hydrogen atoms in the molecular formulae. 2. If the number of carbon atoms in the molecular formulae of alkenes is denoted by N, what will be the number of hydrogen atoms? The molecular formulae of the members of the homologous series of alkenes can be represented by a general formula CnH2n. When the value of N is 2, we get the molecular formula of the first member of the series as C2H2 into 2, that is C2H4. When the value of N is 3, the molecular formula of the second member of the alkene series is obtained as C3H2 into 3, that is C3H6. 1. What would be the general formula for the molecular formulae of the members of the homologous series of alkanes? What would be the value of N for the first member of this series? 2. The general molecular formula for the homologous series of alkynes is CnH2n minus 2. Write down the individual molecular formulae of the first, second and third members by substituting the values 2, 3 and 4 respectively for N in this formula. From the above examples, we come to know the following characteristics of the homologous series. First, while going from one member to the next in a homologous series, A, 1 methylene CH2 unit gets added. B, molecular mass increases by 14 Dalton. C, number of carbon atoms increases by 1. Second, chemical properties of members of a homologous series show similarity. Third, all the members of a homologous series can be represented by the same, a general molecular formula. Use your brain power. 1. Write down structural formulae of the first 4 members of the various homologous series formed by making use of the functional groups in the table. Answer. Here are the structural formulae of the first 4 members of the various homologous series. 2. General formula of the homologous series of alkanes is CnH2n plus 2. Write down the molecular formula of the 8th and 12th member using this. Answer. The molecular formula of the 8th member is C8H18. The molecular formula of the 12th member is C12H26. Nomenclature systems of carbon compounds. A. System of common names. We have seen that today millions of carbon compounds are known. Initially, when the number of known carbon compounds was small, scientists named them in a variety of ways. Now those names are called common names. For example, the sources of the names of the first 4 alkanes, namely methane, ethane, propane, and butane, are different. The names of the alkanes thereafter were given from number of carbon atoms in them. Two isomeric compounds having a straight chain or branch chain in their structural formulae are possible for the molecular formula C4H10. The difference and interrelationship in them was indicated by naming them as N-butane, that is normal butane, and I-butane, that is isobutane. Use your brain power. 1. Draw 3 structural formulae having molecular formula C5H12. Here are the 3 structural formulae having molecular formula C5H12. 2. Give the names N-pentane, I-pentane, and neopentane to the above 3 structural formulae. Use the same logic as used in the names of the isomeric butanes for this purpose. 3. Draw all the possible structural formulae having molecular formula C6H14. Give names to all the isomers. Which difficulties were faced by you while naming? Answer. N-hexane, 2,2-dimethylbutane, 2,3-dimethylbutane, 3-methylpentane, 2-methylpentane. As the time progressed, the carbon compounds became very large in number and their common names caused confusion. A need was felt to have a logical system acceptable to all for naming the carbon compounds. IUPAC Nomenclature System. International Union for Pure and Applied Chemistry, IUPAC, put forth a nomenclature system based on the structure of the compounds, and it was accepted all over the world. There is a provision in this system for giving a unique name to all the carbon compounds. Let us see how some straight chain compounds containing one functional group are given IUPAC names, and let us also see their common names. There are 3 units in the IUPAC name of any carbon compound: parent, suffix, and prefix. These are arranged in the name as follows: prefix, parent, suffix. An IUPAC name is given to a compound on the basis of the name of its parent alkane. The name of the compound is constructed by attaching appropriate suffix and prefix to the name of the parent alkane. The steps in the IUPAC nomenclature of straight chain compounds are as follows. Step 1. Draw the structural formula of the straight chain compound and count the number of carbon atoms in it. The alkane with the same number of carbon atoms is the parent alkane of the concerned compound. Write the name of this alkane. In case the carbon chain of the concerned compound contains a double bond, change the ending of the parent name from "-ane" to "-ene". If the carbon chain in the concerned compound contains a triple bond, changing the ending of the parent name from "-ane" to "-yne". See this table. 1. Structural formula CH3CH2CH3. The straight chain formed is C single bond C single bond C, and its parent name is propane. Structural formula CH3CH2OH. The straight chain formed is C single bond C. Parent name is ethane. Structural formula CH3CH2COOH. The straight chain formed is C single bond C single bond C. Its parent name is propane. Structural formula is CH3CH2CH2CHO. The straight chain formed is C single bond C single bond C single bond C, and its parent name is butane. Structural formula is CH3CH double bond CH2. The straight chain formed is C single bond C double bond C. Its parent name is propene. The structural formula is CH3 single bond C triple bond CH. The straight chain formed is C single bond C triple bond C, and its parent name is propyne. Step 2. If the structural formula contains a functional group, replace the last letter E from the parent name by the condensed name of the functional group as the suffix. Exception: the condensed name of the functional group halogen is always attached as the prefix. Step 3. Number the carbon atoms in the carbon chain from one end to the other. Assign the number 1 to the carbon in the functional group CHO or COOH if present. Otherwise, the chain can be numbered in two directions. Accept that numbering which gives smaller number to the carbon carrying the functional group. In the final name, a digit, that is number, and a character, that is letter, should be separated by a small horizontal line. Usually, numbering is not required if the carbon chain contains only 2 carbon atoms. See this table. 1. Structural formula CH2CH2OH. Here the functional group is OH, that is ol. Its parent name is ethane, and the parent suffix will be ethanol. 2. The structural formula is CH3CH2Cl. Here the functional group is Cl, that is chloro. Its parent name is ethane. Here the parent prefix will be chloroethane. 3. The structural formula is BrCH2CH3. Here the functional group is Br, that is bromo. Its parent name is ethane, and the prefix parent will be bromoethane. 4. CH3CH2CHO. Here the functional group is CHO, that is al. Its parent name is propane. Parent suffix is propanol. 5. Structural formula is CH3COOH. Its functional group is COOH, that is oic acid. Its parent name is ethane. Parent suffix is ethanoic acid. 6. Structural formula is CH3NH2. Here the functional group is NH2, that is amine. Its parent name is methane. Parent suffix is methanamine. 7. Structural formula is CH3COCH3. Here the functional group is CO, that is one. Its parent name is propane. Parent suffix will be propanone. 1. Structural formula is CH3CHOHCH3. These are the two ways of numbering the carbon chain. Acceptable numbering? Both the numberings are equivalent. IUPAC name of the compound is propan-2-ol. 2. CH3CH2CH2CHCl CH3. These are the two ways of numbering the carbon chain. The acceptable numbering is the second one. IUPAC name of the compound is 2-chloropentane. 3. CH3CH2 CH2 double bond O CH3. These are the two ways of numbering the carbon chain. The acceptable numbering is the second one. IUPAC name of the compound is pentan-2-one. Some more steps are required for writing IUPAC names of compounds having more complex structural units such as branched chains, carbon rings, heterocyclic, etc. Study of these will be included in the further standards. At the same time, also keep in mind that there is a practice of using common names of the carbon compounds which are frequently used in the laboratory.